Hi, my name's Ewan, and I'll be going over Lab 5, Choose Your Own Adventure. In my case, I chose to perform the following slinky example. My objective was to model the motion of a stretched slinky falling from static equilibrium on GlowScript, and to compare the observed and predicted data. Pictured to the right is the observed slinky from Veritassim's video. My ultimate result is that the bottom of the slinky does in fact stay stationary in the model, as it does in the video. And to understand this, we need to know some fundamental principles. Of course, there's Newton's second law, specifically the momentum principle, aka F net is equal to dp over dt. This is involved as we need to know the velocity update and position update formulas. The forces in the system are gravitational force, drag force, and tension force. I assumed all forces to only be acting in the y direction, and that the tension force is equal in magnitude to the gravitational force. The gravitational force is equal to mgj hat, and the drag force is equal to b times magnitude of velocity squared times j hat. The free body diagrams on the right show the net forces in each part of the experiment. When the bottom is stationary, the forces acting on the bottom are gravity and tension. When the top of the slinky reaches the bottom, the tension force dissipates and the slinky falls to the force of gravity, which is slightly counteracted by the drag force. When it came to finding the experimental data, I used tracker in the video clip to track the motion of the slinky. Some things to note are that I used the bottom of the slinky as the point mass for the duration of the clip, and that the origin is set at the top of the slinky. As for the experimental measurements, I found the mass of a slinky to be 0.218 kilograms on Google. I used the height of Veritassium to calibrate the length in tracker, that being 1.75 meters, according to Twitter. The initial velocity is 0 meters per second due to the slinky being dropped from rest. I got the initial position, negative 0.3689, negative 1.306, and 0 meters from tracker, and the positive y direction is pointing up. Moving on to the code, the first bit showcases the initial conditions, such as mass, velocity, position, time, and the constants. The acceleration due to gravity on Earth is 9.8 meters per second. The unit vector j hat is positive 1 in the y direction, and the draw constant, much like in Lab 2, was picked through trial and error to be the best value that matched the observed data. The first while loop is for the duration of time the bottom of the slinky stays stationary. In this time frame, which is less than 5.6 seconds, the tension force and gravitational force are the only forces contributing to the net force, and are equal in magnitude. The velocity and position update formulas are applied appropriately using the slinky's mass, g, and unit direction, and the code below the formulas plot the position versus time data. The second while loop is the time when the bottom of the slinky falls to when it touches the ground. In this time frame, 5.6 seconds to 8.43 seconds, the forces acting are the gravitational force and the drag force in opposite directions. All else is the same as the previous loop. Here is my resulting graph showcasing both the observed and predicted data of position versus time for the slinky. In both cases, the bottom of the slinky does in fact remain at the same y position. As explained in the Veritassium video, the gravitational and tension forces have equal magnitude in opposite directions on the bottom of the slinky, until the updated tension force propagates down to the bottom, when it then falls. There are some discrepancies between the observed and predicted data, but that can mostly be contributed to my human error in tracker, such as inconsistent plotting of the point mass and the calibration not being entirely accurate. The other contributing factor could be some unaccounted forces. And I believe that is it. Thank you.